Hello everyone, welcome back to alkaline hydroxide 784, and today in the mathematics series we are going to cover integration techniques. right Unlike the differentiation part, right, it's actually been segmented already, so I'm just going to not finish it in one part, like each of the segments in one part, one episode. In fact, there's only like 3 pointers in this syllabus that include blah blah blah, that part. Yeah, it's only like 3 points to it, so hopefully this will end quickly enough or not, I don't know. So, yes, before we start, let me just, I do realize that whatever I'm going to say may be more relevant for the next episode, but let me just quickly mention that in the previous episode we found out what differentiation comes from, where it comes from, right? Like, you're trying to find the gradient of the graph at a particular point, or at any point, if if you're, because that's what you're usually looking at, the general differentiation equation in a sense. And in this case, for integration, you're trying to find out what would be the area under the graph. But since like, that will only work if you're doing a definite integral, which is in the next episode. So when you're doing a general integration, what you're trying to do is to do the opposite of differentiation. So like, your differentiation is you're trying to find the gradient of the graph, and now in integration you get the gradient and you're trying to find what the graph is from there. So in that sense, that's how integration works. So I'll cover the so-called fundamental part in the next episode, because I think that will make more sense with the definite integral rather than with the general integral. Because with a general integral, you don't really have a start and an end point. With differentiation, it's still possible, because you can still define which point it is by just substituting x to the number. But here you don't really have anything to substitute with, in the sense. Like, you don't have a range, you need a range of values to find out the area under the graph. Yeah, that's why. Okay, so let's just start with the fact that integration is probably the opposite of differentiation, in a sense, in a way, generally. And with that in mind, we will look at how to integrate certain terms. Okay, cool. So of course, this is how they're actually starting it. It says integration of f prime x, and then fx to the power of n, for example. Like, they start with that concept in mind, that you have the differentiation along with whatever term, like, you have the differentiation that you need to integrate back. So if you have something like like this, for example, f prime x times fx to the power of n. In this case, well, I think let's start with something simple. We have x to the power of n minus 1 times n, I guess, n x to the power of n minus 1. How would you integrate it back to whatever your original term was? Well, you know that x to the power of n differentiates to n x to the power of n minus 1, right? So in this case, you just need to bring it back to x to the power of n. So with whatever power of x that you get, you just divide it by 1 more than that power. Like, for example, if it's x to the power of 3, you divide it by 4. If it's x to the power of 7, you divide it by 8. If it's x to the power of 5, you divide it by 6. You get the point. And then you increase the power of x. You make it, for example, x cubed will become x to the power of 4, and so on and so forth. So that's how you integrate the term. And of course, we always need to add the arbitrary constant c, because in differentiation we have all the terms for us, and you have this. If you have a number, you usually differentiate it to 0. But when you're integrating things back, you do not know if there was actually a so-called 0 there for you to integrate back. So we always assume that there could possibly be some constant that, in the original differentiated term, and therefore we represent it with a c. Of course, that c could be 0, so it's not going to cause any harm, so you should write down the c if you're doing a general integration. Definite integration is different because the c is cancelled out, and I'll explain that in the next episode. Okay, so if we bring this higher to f prime x and fx above n, how does it go? Well, since you know the differentiation of fx, right, like that's f prime x, you just ignore it when you bring it back to differentiation, or you just remove that term f prime x, and you leave it as fx n to fx to the power of n plus 1 over n plus 1. Yeah, so that's how it works. It's as simple as that. In the case of x to the power of something, the differentiation of x is 1, therefore you don't see it in any case. And yeah, okay, cool. So yeah, that's what you do when you see a power. So what about for f prime x e to the power of fx? Like for example, if you have I don't know, 2x e to the power of x squared, you just bring it back to e to the power of x squared. Like, there isn't anything much to do with it. So in this case, you just remove the fx prime f and leave the fx e to the power of fx part alone. And you can put your c in as well, the arbitrary constant. Okay, then we move on to the next bunch of things that you can integrate. Sine square x, cosine square x, tangent square x. Okay. Well, here's the easy way of doing this. If you have a sine square, cosine square, or whatever square, right, you should try your best to convert it to a linear thing, right? Because yeah, that makes, well, actually, since this is like when you're integrating, you can integrate sine squared, you can integrate sine x cosine x directly. So since you can do that, you can always convert this to 1 minus the other square. In any case, wait, no, don't do that, sorry, actually don't do that. This is actually better, because if you, if in other words, if you have something like 1 minus sine square x, then convert that to cosine square x, because that's easier to integrate than 1 minus sine square x. Yeah, in a way. So cosine, so for example, sine square x would become, well, it would, you would technically think of it in terms of no, sorry. Yeah, now I remember what you're supposed to change it to. You're supposed to change it to sine 2x. I'm sorry. I'm so sorry. Yeah, so you should change your sine square, your cosine square to sine 2x or cosine 2x. And from there you can integrate it normally, because you know, if you integrate sine x, you get negative cosine x. If you integrate cosine x, you get sine x. So you can use it with your sine 2x or cosine 2x, because it will just become, like for example, if you integrate sine 2x, you just get negative half cosine x. Oh, sorry, cosine 2x, yeah. And that's a lot easier than trying to integrate sine square or cosine square x. As for tangent square x, you can make it secant square x, and you can then use that to get tangent x in a way. So for example, tangent square x, you can, since tangent square x plus 1 is secant square x, you can convert it to secant square x minus 1, which would then become tangent x minus x. Yeah, that's basically how it would work. And of course, add your arbitrary constant c. That's important. Okay. Oh yeah, when you're writing down your constant c, I believe in the exam they don't really need that, but by right, you're supposed to say that where c is part of the real numbers, basically. You don't want any, you know, imaginary numbers in here, you know. So basically what you write is c, what's that thing called? The thing that looks like a e but is not an e, you know, is part of real numbers. Yeah, just write that down. Okay, so the next part is the Oh yeah, sine mx cosine nx, cosine mx cosine nx, and sine mx sine nx. Sorry, I guess that sounded like gibberish. Okay, so in this part of the line, it's like you get a combination of sine and cosine in your term, and that's actually better because you have both. So in that scenario, when you have your sine mx cosine nx, you can well, if it's, for example, if it was the same, if m and n were the same, then your job will be so much easier because it's just sine and cosine. So you can pretend like one of them is the differentiation of the other one, and then you can just increase the power of the other one in the sense, or you can just change it to sine 2x. That's always a possibility. But in this scenario, when you have a different m and n, you have to use your trigo formulas. You know, the what's that thing called? The one with the p and the q, that one. Yeah. So for example, if you have sine bracket this plus this, right? Right. Yeah. So okay. So if you have, for example, sine x, wait, so sine x sine 4x would be equivalent to sine of x plus 4x over 2 plus cosine 4x minus x over 2, that kind of thing. Yeah, that one. I don't think I'm telling this correctly. Yes, this is the one, sorry, you can just look at your MF26, don't bother. Okay, so sine p plus sine q is equal to 2 sine p plus 2 over 2 cosine p minus 2 over q over 2. Yeah, actually I'm not too far off. Okay, so this equation can be used when you're doing your when you encounter terms like this, if you have your sine cosine with two different coefficients for the x, you can use this formula and you can split it into a addition or subtraction, which is of course a lot easier to integrate in this case. So for example, if you have your sine mx and cosine nx, then what you would do is you look at your MF26 and you realize, oh, it fits the first one, which is sine p plus sine q. And that would be, you imagine your mx as your p plus q over 2, and n as p minus q over 2. So how do you get your p and your q? Basically, for the p, you just plus the two of them together, m plus n over 2 in the sense. Because m is p plus q over 2, so if you plus m and n, you get p. And if you want to get n, you have to have m minus n. Yeah, if you get q, sorry, to get q, you m minus n. I'm pretty sure that right would be a lot more clearer than this. So your final integration would be half of sine m plus n, of m plus n plus sine m minus n, and of course the c, important, the c. And likewise you can do this for the rest of the terms. If you have your cosine in front, you can use sine p minus sine q equation, or it depends on whether your p and q are positive or negative. That's not important. For the cosine one, you can use the cosine m, cosine nx. You can do it for your cosine p plus cosine q. You get sine mx sine nx, then you use cosine p minus cosine q. Just use those formulas and then just convert it and then do your integration. I hope that's easy enough for you. If you are confused about this, then I don't know, PM me or something. I hope that works. Okay, so the last bunch of stuff in the first point Yeah, actually there's only 3 points, but the first point is just too many things inside it. So the last part is all these fractions, you know, the one with the squares in them. For example, 1 over a square plus x square, then 1 over square root of a square minus x square, then 1 over a square minus x square, and 1 over x square minus a square. Of course, if you're very kiasu and you have like so much of time left in your exam, I don't know, maybe you might. I'm not sure how your exam is gonna be. You can do this a long way using a substitution. But actually that's the next point, integration by a given substitution. And I actually learned how to do that in my RGS Maths RA. So it's not that hard, but it is a bit annoying because, you know, why you have to do that when you have this so beautifully available stuff right in your MF26. I mean, if you're looking at it from an exam standpoint, then you should probably use your MF26 and save your time. But if you have some free time and you wanna learn how to do this, then go ahead. I'm fine with it. It's actually quite interesting to do it. Okay, so you know in your MF26 you have this part where you have your derivative for your sine inverse, cosine inverse, tangent inverse, and then accordingly you have integration for the, you know, the stuff that's been derived, the 1 over x square plus a square. So you just need to use those formulas and it should work. You shouldn't go anywhere wrong in a sense. The only thing you need to take note of is when your x is not just x, it's just like 2x, or sorry, 4x squared for example, then you instead of x you consider it as 2x. Or if it's like 9x squared, then you consider it as 3x. So you substitute x for 3x in the sense. And then you have to integrate that in a way. Do you? Actually, I don't think so. Okay, you don't really need to integrate that. Just take note of that coefficient. Yeah, so for the exam, this is all you need. You just need to look at this and then just write it down. Just apply what you see in the MF26. But since I am a maths nerd, okay, actually I'm not really a nerd. I just like, since I think this is useful information, let me just tell you how to do it with substitution, you know. Anyway, the next point is about integration by a given substitution. So why not? I'll just show you how to do this with a substitution. So let's just take one of them. Let's not cover everything. It's not worth it. Okay, so that's the easiest one here. Let's do the one with the 1 over square root of a square minus x square because it shows sine inverse. So I think that's a lot easier. I hope. Okay, so for this one, you must think about it. If you are a square minus x square, so how do you make it something that can be integrated? So in this case, well, it is a square root, but since your a square is a whole number, it is a number, you can use sine squared or cosine squared in the sense. So for your x, you can substitute it as sine theta or cosine theta and add in a coefficient in the front because you have a square. So, but we're gonna go with the case where it's 1 because that's a lot easier to deal with. But if it's something like 3 squared, then you put it as 3 sine theta or 3 cosine theta. So for the most basic example, we will go with 1 over 1 minus x squared, the square root of that, sorry. And in this scenario, you would substitute x as sine theta because sine theta is nicer, I think. I don't know. That's your decision to make. So then x squared would be sine squared theta. Okay, this theta we'll deal with it later. So just keep it as it is now. That's your substitution. And when you substitute x for sine theta, then your 1 minus x squared will become cosine squared theta, right? And the square root of that is cosine theta. And on the side of your integral, you need to change, you need to add in the d theta because you're now introducing that theta in a sense. And I hope I write it down correctly because I don't remember. I can't really tell it out. It's too confusing for me to tell it out. So yeah. So once you introduce that, now your thing boils down to 1 over cosine theta, which is just secant theta. And yeah, that can be integrated using your, I mean, you don't really need to integrate it. If you want to be extra kiasu and not at all use the MF26, then your secant theta can be something like I don't know. Yeah, there's a way to get it. Like you can use your ln to get the answer for secant theta. I might write it down here because I cannot think about it right now. Honestly, I'm not kidding you. I really cannot think about it. But the one in MF26 says that secant theta is ln of secant x, secant theta plus tangent theta. So in this scenario, you must make sure that your theta is between negative pi over 2 and pi over 2. Yeah. Oh yeah, do take note of these limits, the ranges, because that's important when you're doing questions or application questions. Yeah. And maybe you should write it down when you're writing your integration. You must say, oh, x is within this range, just to be extra careful about it. And I think that's also required. And of course, don't forget your arbitrary constant. Okay, so yeah, so now you have your integration is done, and you have ln secant theta plus cosine theta. Okay, just kidding, that's not how it goes. Haha. Okay. backtrack. Okay, so you're now at secant theta, right? But you have your differentiation of d theta, that part, and for that you need to differentiate the you need to find dx over d theta, and that would be, well, since it's sine theta, your differentiation will be cosine theta, and therefore you will get cosine theta over cosine theta times secant theta just equals to 1. Yeah, that's pretty much it. Yeah, like what? So your final integration is x. So what is x in this case, in this scenario? X would be, well, you can just draw a triangle and you have your theta in one of the angles, and since this is sine theta, your x is opposite. It's the opposite line in the sense, and you have an adjacent line, and you have 1 as your hypotenuse. And wait, no, not 1. Yeah, actually 1 can. 1 is your hypotenuse. Yeah. Okay, so yeah, so sine would be opposite over hypotenuse, right? So that will be x over 1. And in this scenario, if you look at MF26, you get, x over a. It's the same thing. If your a wasn't 1, it would be the denominator. And you're finding the x, right, not the angle. So your answer would therefore be sine inverse of x over a. Yeah. So that's how you actually get it. It's actually not that hard to get. Yeah. I hope whatever I write down would make more sense of whatever I'm saying, because it's quite hard to say it out in words. Yeah. So you can do this for literally any of the other fraction things and it will all work. It's not that hard to do. And if you are free, you can just try it out and amuse yourself. Okay. So now that I actually covered how to do a substitution integration, I don't think I really need to worry too much about the point that says integration by a given substitution, because in this case you just you just follow what substitution they give you, and you find the differentiation of what you're substituting. Like for example, if you substitute x equals to sine theta, then you find out what dx over d theta in the sense, and you just incorporate everything and make sure your presentation is correct. Okay, so let's move on to the last part, which is integration by parts. Integration by parts will, well, okay. Right, so integration by parts would mean that you have, when you're doing differentiation and you get two different terms from like a multiplication, you have your uv, then you get your, what is it, the du or dv, du or dx times v plus dv or dx times u. So you're basically doing the opposite of that. That is what integration by parts is. That's pretty much how it goes, kind of. So how would this work? For that, you actually, I need an example. I need to find an example. Let me just find some example I can use. Sorry. I'm like just searching for examples now, so I can just, because actually I can just represent this with terms instead of examples. Okay, so first let me tell it to you in terms. So in terms, what you would do is you would have something like yeah, so you have uv becomes v prime x times u plus u prime x times v, and you need to bring that back to uv in the sense. So when you're integrating the entire term, yeah, integrating the entire term, and you want to find only one of them. You only want to find, for example, u or v or something, I don't know. You basically just need to manipulate it a bit and you get your integration by parts equation in the sense. So so for example, if you have yeah, so you have that entire term, right? And then you're trying to integrate. Oh, okay, now I get it. Sorry. I kind of forgot exactly what the equation looks like, but okay, now I think I know how to explain this. Okay, so you have uv equals to u prime x times v and v prime x times u. So if you integrate everything, like you integrate throughout by x, you get integration of uv dx will be equals to whatever you integrate in, that part, and whatever integrate in this part, right? So for the u prime v, you will then get u integration of v, right? And then for the v prime u, you will get v integration of u. Wait, what? Okay. I think I need to write it down. Okay. So yeah, just watch me writing it down for some time. Or I've already written it down because I wasted too much time talking. So the final thing that you get from this is the integration of uv dx will be your u integration of v minus the integration of u prime integration of v. So what does that become? Yeah, it just becomes a weird mess. So in order to do this, in order to execute this thing, you first need to identify your u and v. That's the important part. So for example, if you have something like I don't know, x sine x, that's pretty simple. So you need to find one that you're willing to integrate and find one that you're willing to differentiate, in a sense, So which one is easier to get rid of? Of course the x. So you must differentiate the x and make it 1. So in order to differentiate, so that will become the I don't know, the u, I guess, and sine x will be the dv or dx. Yeah, I prefer putting it that way. So you would then get to this. So what you do then is you integrate sine x, which will give you negative cosine x, and you times it by x, of course, because it is just u. So you get negative x cosine x, and then you minus the you still have your v, right, your cosine, negative cosine x, and for x you differentiate it, and so your integration will be that of negative cosine x, and then next you can just integrate negative cosine x and you'll get your final answer. Yeah, that's the point of integration by parts. Okay, so I think the more important thing to cover here is when you encounter a question where you have no choice, but like even when you integrate it through integration by parts, you get another thing that you need to do integration by parts on. So in that scenario, I suggest that if there's a trigonometric function, you use that as your, you integrate that twice or something like that. And once you do it, you will get a repeating term. And when you get the repeating term, you can use it to minus off on both sides and use it to calculate your final integration. So what I mean would be something like your sine x. Oh, sorry, not integration. Wait, I mean you could integrate or you use that to differentiate, or I don't know. I kind of forgot what the example is. Oh my gosh. It's been so long since I did these questions, but like you get the point. So like for example, you have e to the power of x sine x, then you definitely need to do this because honestly, your ex is forever going to become ex whether you integrate it or differentiate it. It's not gonna go anywhere. So instead what you do is you use your sine x and you manipulate it. So in the next step you get cosine, and then you can redo it and you get another sine. And then from there you can use some algebra and you can find out what's the integration of ex sine x. So I'll probably write it down somewhere here in the paper. Yeah, I think I'm taking too long just for this, so yeah. I hope I kind of covered most of what is required. If there's any integration that you think that you do not know yet, just go and look at the MF26. It should be there. The more weird ones are there usually. And there are other ways to find the integration of certain complex terms, which is one way is to use reverse, it use like a reverse differentiation kind of method. So like for example, for secant x you can do this, you can pair it with another term or something, and then you can do a differentiation on that. Like for example, if you're trying to do ln x or something, I don't know, you're trying to integrate ln x, then what you can do is you can instead integrate like a product or something, because when you differentiate ln x, you have to do x ln x or something. You differentiate x ln x and you get what, for example, ln x. Yeah, you have to first differentiate, then you do the integration later on. So if you differentiate x ln x, you will get ln x plus 1, right? Because if you differentiate ln x, you'll get 1 over x, yeah. So ln x plus 1. So if you want to integrate ln x, what you need to do is, you can integrate ln x plus 1, right? Ln x plus 1 will give you x ln x. But if you're just integrating ln x, then you just bring the 1 over the other side, which would mean you will get x ln x minus x. So that's actually the integration of ln x. I hope you understood what I meant. So likewise, you can use it for your complicated terms if there's anything that you really have trouble integrating. Yeah. I hope I told enough because it's already 34 minutes, so I somehow this was only 3 points and yet I spent half an hour talking about it. I guess I like to talk about this. Okay, fine. Okay. I hope you found this episode useful because I did talk a lot, so yeah, must be useful at least for 5 minutes of it. I don't know. If you did, please press the like button and subscribe. And with that, I would like to say thank you and bye.